Good afternoon, everyone. It's 2:30, and I'd like to welcome you all to the Native App Development in a Multi-Platform World presentation. My name is Jeff Jackson, and I'm here with Eric Ito. We're going to ask that you share your feedback for our session in the app. So Eric and I work for Esri on the apps team. We've been working primarily on mobile apps over the last several years, and you may recognize some of these apps in this slide. I think the focus for us right now, actually for the last couple of years, has been ArcGIS field maps. And we are currently working on a rewrite of field maps. It's a pretty massive undertaking. And what we're going to present today is really some insight into the approach that we take when we build apps. We're building our apps on top of the Maps SDK. So I want to ask a couple questions of the crowd. Raise your hand if you use the Maps SDK currently. And raise your hand if you're building apps for iOS. How about Kotlin, Android? Okay. And anything else? Any other platforms that we forgot about? Windows, okay. Yeah, so we've been building geospatial apps for mobile devices going all the way back to the original iPhone and even back into Windows Mobile, and even before that with those little, I can't even remember what they're called, PowerPC. I mean, there was a whole bunch of stuff. So we've been doing this for a long time. And where we're at for our customer base is that Android and iOS are the two platforms. And the typical approach that you might take and that we took for several years on these apps was building the app on one platform with one team and building the app on the other platform with another team. And the teams may or may not communicate. A lot of times, actually pretty typical for our team would be that the iOS project would be well ahead before the Android project started. And Android would always seem to fall further and further behind. So this is just something that we had always kind of learned to accept, but we thought, well, maybe we can do better than that. So there's a whole bunch of different approaches to building, a single app for different platforms, and list out a few of these here. This isn't new, right? This has been going on for years. Actually, when I started at Esri, the first project that I worked on was a product called ArcView, and it ran on a whole family of Unix boxes using different flavors of X windows, and then Motif and what's the other one? Anyway, I can't even remember. And then also it ran on Windows, so Microsoft Windows, and on the Mac. And we used a product called Open Interface from a company called Neuron Data. And the dream there was you actually had the same UI toolkit that you were working on, but you were writing, you had a code base for each platform, but the code could kind of take the same approach to delivering the UI. And then some of these other packages that we see listed here have different approaches. The dream, of course, is, wow, I have one code base and I can just, deploy it to different platforms. And that works pretty well for certain types of apps, right? Simpler apps or apps where you don't necessarily have to conform to the user interface guidelines for the platform. We saw a demo actually on the stage in the plenary of a Flutter app, and they actually had it side by side, and you could see that it looked exactly the same, Android and iOS, but neither of those apps looked like an Android or an iOS app. So for some applications, that's okay. One other little caveat with using a technology that sits between your app and the operating system is that the company that's delivering that technology better be around for a while. So we've seen this with this slide we updated from our talk last year because it had Xamarin and Qt on it. I hope you don't have a lot of investment in those technologies. We do in Esri and some of the other apps that we build. So why native? So actually I wanted to say that we've chosen to go native. So we aren't using any real enabling technology. We are using a third-party app in the Maps SDK, and that does deliver itself on a whole bunch of different platforms. But we chose to use native for a long time just because we wanted that superior user experience. We wanted people that use these apps that we build to have them behave the way the other apps on their devices behave. And, probably some of the most popular apps that people use are the apps on their iPhone that Apple built, or their apps on their, Android phone that Google built. And so we want to follow the guidelines that those companies have sort of put forth for building apps on their platforms. Building apps in that way without any kind of middle tier, we get more of a performant, at least, we have the opportunity to have better performance. We can always use whatever the latest release for that operating system has. So every year we go to WWDC and Apple talks about, hey, we've got this new thing that's coming out. Well, we can tap into it as soon as it's available. We don't have to wait for the third party kind of wrapper for it. And then developers like working with these tools. They like being able to go and get help on the internet. They like to be able to use the native IDEs. It's like the path of least resistance for developing for a particular platform.
So does native development work? So Jeff kind of described how we used to work. In some cases, we were staggered. iOS was ahead and Android was behind. In other cases, in the best scenario, we'd have feature teams that were working on the same capability at the same time with the same inputs and the same designs and the same requirements. But they would both go off and interpret those, the solutions differently, and we'd end up with slightly different results. And so we'd have bugs on one platform that didn't exist on the other, bugs at the application code layer. And the QA that needed to happen would happen multiple times at different instances instead of all at the same time across both the platforms. And so, we started thinking how can we do this a little bit better? So the Maps SDK, when that was announced, it was a pretty big change for us because we knew that we were basically going to either have to spend a ton of time retooling our existing app code to somehow sit on top of this large set of breaking changes, or we'd have to rewrite the whole thing. And when we started to think more about it, we thought that maybe it was the opportunity that we wanted to really fix how we build these apps. And so the Maps SDK was rebuilt specifically with Swift and Kotlin for Swift UI and for Jetpack Compose. And this is right around the time when we had been spending quite a bit more effort trying to figure out if these declarative UI frameworks really would work for us. And so we started to think about how we could build these components, these different feature capabilities across the platforms with designs dedicated for each platform, but still have, the business logic be the same, the algorithms be the same, without all of this wasted effort that we had before. And so as we started to rebuild field maps on the 200 SDKs, we kind of set out some goals for ourselves. The first goal was to have a more modular approach. So we really wanted to focus on having really fast build times and as few dependencies as possible across our features and our modules. And so currently, this is a couple snapshots of our current implementation, and we have about 80 different modules on each platform for various things. You can see account analytics, authentication, everything kind of spread out into these compartmentalized pieces that could be individually tested. So this graphic here is a build timeline from our iOS app prior to the 200 SDK. And that application, there were frameworks that we used, but we had significantly fewer, and they were much larger, multiple features within the same framework. And so you can see these gaps in the build timeline. That's waiting for dependencies that have to build before some new module can build. And that means that those build times are much longer. So when you're making some tweaks and building and making some tweaks and building, you lose a lot of time. So here's what the build timeline looks with our new approach. And you can see almost all of the modules are able to build in parallel. And we have one gap at the far right, and that's actually something that we've been battling for a while, which is specific to Swift UI and toolbar content. But that's at the highest tier. So the only thing that's waiting on that is copying over bundle resources and doing the code signing to actually get it onto a device. We're not waiting for all these other modules to build. So it's way more efficient. So the next big goal was to improve our collaboration between developers. So we talked about developers having this thing that they needed to build and kind of loosely talking about high-level ideas and going off and doing it separately. We wanted to get rid of that. And so now the way we do this, or the way we're limiting this duplicated effort now, is by having those developers talk more up front. And instead of them both going off at the same time and trying to implement it at the same time, we implement it on one platform first, get it tested, make sure everything's good, get it merged, and then we port it to the other platform. So we might start with Android for feature A, and then when that's done, iOS ports it. And then for feature B, we may start with the iOS developer, and they get that done and merged, and then the Android developer would port that. So the third goal that we had, now that we were working with Swift UI and Jetpack Compose, was to work more efficiently with our designers. So in the past, we'd have our designers give us designs, and we'd try to implement them as close as possible, be pixel perfect, but inevitably we'd have issues with colors or spacing or some interaction that wasn't quite right. And so we wanted to improve on that workflow. Well, Swift UI and Jetpack Compose both enable previews in the IDE. And so we thought maybe we could take advantage of that to iterate on the UI when we're implementing it, but then also give designers a more approachable way to make these changes themselves. And so we were actually doing that today. We have designers that'll go in and they'll make changes. Could be as simple as spacing, or maybe accessibility. I mean, we have designers that are going in there now and adding support for dynamic type and adaptive layouts. So if you have larger text size, that layout may need to adjust because maybe you can't stack something horizontally. Maybe it needs to be vertical. So they can go in there, mimic that environment, and make the necessary changes without having to do a full round of generating a build, installing it on a device, and continuing with that cycle. So the last big goal was to have more comprehensive testing. So previously, the only testing we had was some light automation and manual certification, manual QA. And so we really, really wanted to have unit tests. We wanted to be confident in the changes that we were making to our code and not have to rely on those manual QA efforts to catch regressions. We wanted to find those bugs faster, fix them before they even land in main. And so to be able to write those unit tests, well, we have to be able to mock out our dependencies. We have this maps SDK with objects that depend on URLs to remote resources and data JSON coming from feature services. And without being able to mock that out to mimic the cases that we're trying to test, we wouldn't be able to be successful. So on the Kotlin side, there's a library that we use called mock-k. Does 99% of the stuff that we need to do. On the iOS side, since the SDK is built with Swift, mocking becomes a lot harder. You can't use any dynamic runtime tricks to mock out objects. And so what we ended up doing was using a product from Apple called Swift Syntax to generate an abstraction layer around the Swift SDK. Basically, we generated protocols for the entire surface area and then accompanying mocks. So that in the test, if we need to mock out a locator, we can give it a specific mock that returns exactly the results that we want. And so that basically enabled us to start to work on those unit tests. Going beyond the unit tests, we always relied on manual testing. And aside from being time consuming, it's just not efficient. And so we wanted to rethink how we were doing the automated UI tests. So I mentioned that previously we had some variation of this, and it was relying on a third-party solution. And that third-party solution, it was easy to write the tests. It was a common language that it was really easy to learn. It wasn't a native Swift or Objective-C or Kotlin or Java. It was something like JavaScript, I think, or maybe natural language. But it had some downsides. First, it relied on real objects that were going over the network. And so when you're making network requests in a testing environment, things happen. Like latency, network latency, services may be unavailable. You might hit random timeout errors because something just isn't responding as quick as you expected it to, and now you have these test failures. And now you're stuck with trying to figure out, well, is that test failure a real failure? Did something regress? Did we introduce a bug? Or is it just failing because the server didn't respond in 2 seconds, it responded in 5 seconds? So we really wanted to improve on that. And so the Maps SDK team, they had similar concerns about network, and they built this library called Deja Vu that is essentially a way to intercept network requests so that you can return a response. And so the way we use it is we'll run the test against live data. It'll record all of the network calls that go out and all of the responses and store them in a database. And then when we want to run the tests on our CI environment, we're using all of that data locally. So we don't have to worry about network latency, timeouts, all of the network issues that could come around. And so those tests run a lot faster. They're a lot more stable. And now we can actually rely on those UI tests. I forgot to mention that once we tested this particular library out on iOS, we ported the same library to Android and then started filling out our Android UI tests as well. So now we have them both tests on both platforms.
Okay, so we're going to end the show. We're going to change this to entire screen. Okay. We're going to close that. And there's that. And this. I'm going to close this. This. All right. So, smaller. So, in order to sort of demonstrate some of the actual code, and what we decided to do is rather than have a, there you go, you good?
Yep.
Rather than like try to pull up code from the Field Maps app or something like that, we've built a little sample app that is following the patterns that we use, and then we can talk about those things. And the nice thing about that is we can make that source code available if someone wanted to take it and kind of study it in a little bit more detail. So the app that we built is this little mapping app that supports search. And what you're going to see on the left is the iOS simulator. And on the right is my Android device being mirrored. And so basically this app's pretty straightforward. You can see a map. I can tap this little button on the bottom to show a search screen. And then I can, start searching, or I can, why don't we just go with a previous search. So I'm going to look for pizza, and it's going to use the area of the map as kind of the seed. It's going to hit the geocode server, and here's the result. So we got a bunch of pizza here, and I don't remember which one we're going to look at first.
Shakey's.
Yeah, let's go check out Shakey's. So if I tap on Shakey's, then you see all of the results are added as graphics on the map. Shakey's is highlighted. We can go back. We can pick the Pizza Hut. And then you can also just interact with the map. So I can, tap and select different results. So let's go back to the search screen. We'll clear the search. Another thing that this does is it actually has suggestions. So as I type, you'll see suggestions sort of dynamically appear underneath. And then we can pick one. Let's go to the restaurant. Yeah. So that's it. It's a pretty simple app, but I think it's enough for us to dive into some code and have a little bit of context. So let's go back to extend display. And then let's go back to the slides and presentation. All right. So that was that. Okay, so one of the key things that you kind of have to know to work in this environment is that we use this architectural pattern called MVVM. And it's very popular. It's been around for many years. When we chose to go to declarative UI, MVVM was just a natural thing to do along with it. If you're not familiar with MVVM, I'll give you a real quick lesson on it. Basically, what does it stand for? First, model, view model. So all of the code that you write is either going to be, you're writing a model, you're writing a view, or you're writing a view model. So the model is the business logic and the data that sort of feeds your app. And then the view is the UI layer. It's it's responsible for the presentation and also for initiating events, like when someone taps a button. And then the view model is kind of the glue in between. It's going to expose properties that the view can bind to. So, the label that you're going to put on that button. It's going to respond. It's going to have functions that the view can call, like when your button gets clicked, go, retrieve the pictures. It's going to contain the application state. So the view models tend to be where all the things really happen, and we want the views to just kind of react to them. And we're like, if you were to take apart the Sequoia code base, Sequoia is the project name for the rewrite of field maps, you're going to find view models all over the place along with their corresponding views. So every screen has a view and view model, every dialogue, every bottom sheet content, etc. So a real simple example, is that video running? No, run it. This is actually just a quick demo from using field maps, showing a feature's attachments. They're displayed in that gallery at the bottom, and then when you tap on an attachment, it gets downloaded, and then the display of it changes. So the model in this case is the attachment, so in this case it's a video, and then the view is the attachment view gallery, which is responsible for that horizontal scrolling thing that shows all the attachments for this feature. It's, in this case for the video, it's displaying initially the size of the video, and then it's later on, once it's downloaded, it's displaying the duration of the video. So it doesn't know anything about that. It just knows that there's a piece of text that needs to be displayed. It's the view model that actually does some work here. So it retrieves the attachment information initially to populate that gallery view, and then it calculates the size of the attachment, and then when it's tapped, it downloads the attachment, and then it calculates the duration. And so it's serving up the size and the duration as a text property that the view can bind onto. So that's just kind of the basics of MVVM. So we talked about previews making it easier for us to rapidly iterate on the UI without having to build and deploy the app every time. So the previews, what a preview is, and we'll look at an example in a second, but a preview is basically just a function that's calling that composable function, in the case of Jetpack Compose, or that view in Swift UI. So it's just a function that can say, hey, do that view thing, right? And it's because it's supported by Xcode and Android Studio, it lets you see, the UI while you're still coding. And that makes rapid refinement of the UI possible. So we're going to demo a preview. So let me, again, do this switcheroo. That. Where is it? Oh. All right, so the app that we looked at has the search view, which is this guy here. So that's a composable function, and it can display either previous searches or suggestions or results. And so that's the logic here, where it says, okay, if we have results, then we're going to show the results list. Otherwise, if there's some suggestions, we'll show the suggestion list. Otherwise, the recent search list. So let's go look at the search results list. So that's the part of this search view here on the right, the actual preview, which is the list, just the list part. And if I wanted to change something about the list, like I might want to put more space between the results, I can change the padding, and then it instantly changes. We might want to say, give it a background color. Yeah, like light gray, that sort of thing. And then border color, sure, color.gray. Yeah. So that's how quickly it works. And because, this is a simpler example, but it's the same kind of performance working on the Sequoia code base, because again, like we've got these modules and we don't really have to recompile anything other than the composable functions that we're working with. Do you want to show the?
Yeah, show Xcode.
Yeah.
All right. So here's the search view, but on the Swift UI side. Here's the list with results if we have search results, the recents list, and the suggestions list. So we'll go back down to the search result list, and we'll make a similar change. So let's see, you added some padding. So we'll do so you added 40, space those out. You can see they get spaced out farther. I didn't really like that background thing, so I'm just gonna add a border, but I think you did gray, and we can do a width of 5. And again, updates pretty darn quick, so you can see how those changes can be pretty easy to work through.
Yeah, and I mean, one thing that's obvious just watching it is that the one area where we don't really make any attempt to, well, not any attempt, but where we really can't achieve true alignment between the two platforms is at the level of the view, right? Because Swift UI is very different than Jetpack Compose. But we actually, that's the only place where we're like okay with that. When we start looking at view models and the rest of the application, that's where we can have real good alignment. All right. extended display. And now we go back. Okay. So this is a real simple example of preview. We have the simplest view model you can imagine, called sum view model, which has a single property. The view, which is what we see displayed in the preview, the view is dependent on that view model. So we pass that in as a parameter, and then we access that property to throw some text on the screen. And then for the preview, in the syntax in Compose, and it's similar on the Swift side, is you have at preview, and then it's another composable function with no parameters, and it takes it calls that sum view and passes in an instance of the view model. So it creates the view model, passes it to the view, and it gets drawn. So for real view models, or more complicated view models, it can be difficult or impossible to actually instantiate them while you're sitting there at design time writing code. So, just to show, like for our app, there's the search view model. It has a number of constructor arguments, which would be very difficult or impossible to create while you're in the IDE. So like the locator task is a Maps SDK concept, and for it to even be created, that's a difficult thing. But then for it to do anything, you have to go off, you have to make a network request or whatever. And then things like a spatial reference, and the application itself, those things become difficult. So how do we get around this problem? So the approach that we've taken is to introduce an abstraction. And so that's an interface on the Kotlin side and a protocol on the Swift side. And so the view model actually is just an interface. It's a contract which says, hey, here are the properties and methods that are going to be necessary to drive the view. Okay, so if you look at the examples here, you can see the text, right? There's a property called text. On the Kotlin side, it's a mutable state flow, and on the Swift side, it's a mutable string. The text is the when I was typing in the search, like you could type in pizza or whatever. That's this text. That's where that's going to come from. And then you see the results. So after a search is complete, we've got a state flow that returns a list of places. There's a Boolean property while searching is going on. There's the recent searches, the suggestions, and then there's the methods that view needs to call. Like when you tap on something, when you tap on the search button, we're going to call search. When you tap on a suggestion from the list, we're going to call search suggestions. And then when you hit clear, we're going to call clear, and there's selection. So all that stuff that the view model actually can do is just abstracted into an interface. And what that allows us to do is to, for previews, either create, in the case of Kotlin, it's an object. In Swift, it's a class. But we basically create a preview view model. And they just have simple, values that the view can bind to. So you kind of seed the view with stuff that's going to look right so that you can start playing around with it and get the layout exactly the way you want it. So like in this case, we're going to set search text to be places, and we're going to have some preview places that show, some places that would show what places on the map might look like. So it's a pretty handy way to get around that problem. And the naming conventions that we use is that you notice that both the preview search view, the preview search view model and the anonymous object here both are implementing the search view model interface. So throughout the code where you're interacting with view models, you're actually always interacting via an interface. It's just at the instantiation where we see like the concrete implementation. And here's what that looks like. So it's just search view model with impl at the end. So that's the naming convention we use. You'll see that in this case, the classes have the same name across both languages. The base classes differ slightly. We use an Android view model base class, which is just coming from the Android SDK, and then it's a view model on the iOS side. The other difference here is just the language is different, right? So Kotlin has constructor arguments, and you see those listed out. They're actually pretty handy. We'll see those same properties in the initializer for Swift in the next slide. The other thing to note is that for observable properties, so if you have a simple property, you can, like if you had a string property, the view can get access to that string, but if the string changes, the view doesn't know about it. So anything that actually we want to drive change in the UI has to be an observable property. So on the Android side, we're using state flows, and then we use this published properties on the iOS side. So here's the initializers. In Kotlin, the initializer doesn't take arguments because they come in on the constructor arguments. And then on the iOS side, that's where we pass those things in, and we saw before. We just sort of set them up. And then both of them are going to observe one of their own properties. So in the example here, we're observing the text property, and we're saying, oh, if the text changes and we're not already searching, we should go find suggestions. So that's kind of what's happening there on both sides. So now we'll look at just one of the functions in the search view model just to get a feel for how things line up. This is the search. So this is what actually kicks off the search and talks to the locator to get results. So we'll do this over the course of 2 slides. The first slide is kind of the setup slide. So the logic is the search text empty? If so, we don't do anything and we just bail. Otherwise, we clear out the suggestions. Then we look and see is the search text that's coming in something that we've already saved off as a recent search. If it hasn't, then we're going to add it so that it's there next time. And then we set up the geocode parameters. The one interesting thing about setting up the parameters is when we search, we want to search based on the current visible area of the map, right? We want relevant search results based on where the map is. So we actually are using a delegate here, and that's the way that the main view model can work with the search view model and say, hey, I know where you need to do the searching here. So this delegate that was passed in to the constructor of the search view model is actually access to get the search location. And then the second part of search, we launch so that we can make some asynchronous call against the locator. We're going to set some state. So we're going to set a property to say we're searching. That's true. We're going to update the search text that's displayed. Then we're going to clear the results. We're going to tell the delegate that we cleared the results. And that's the way the main view model can react to that and clear the graphics off the map. And then we call geocode on the locator. And you can see that that's a little different on the 2 platforms. On Kotlin, geocode is a suspend function that returns a result. So we can key off success to do stuff with the results and get them into a format that we want. It's different on the iOS side because on the iOS side, geocode can throw. So here we're catching it. We're doing a do catch to deal with the error conditions. And then in both cases, once we've gotten a successful result, we actually turn the geocode result list into place results, which is just a class that's specific to this app. And that's what we set into the results property. And then again, we tell the delegate that the places were found so that they can be added to the map. And we set searching false. So I don't know if it came across in the demo, but while you're searching, there's like an activity indicator that displays that something's going on. I keep hitting that arrow and it keeps not going forward, but I don't learn. The last piece I want to show from that is the search delegate. So I talked about this a little bit, but we define an interface that allows the main view model to communicate with the search view model, and that's the search delegate interface. So in one case, it's an opportunity for the main view model to provide the search location for the search, and then the other three functions are actually so that we can communicate what's happening with the search itself.
All right, so Jeff has shown how we can line up our implementation code. And so I think next we should just show how we can line up our unit test code. So these tests that we're going to write, these unit tests, like we talked about before, they're our safety net, so that we know when we're making these changes, we're not going to go break other things that we're not working on, or that they won't later be broken by other changes. So here's an example of one of the tests in Mapster. This particular test validates that for some given text input, before the users actually tapped search, that we get suggestions back. And so you can see the Kotlin code on the left lines up almost identically to the Swift code on the right. We start by creating a mocked locator that returns some suggestions, which are also mocked results. And then we pass that mocked locator into a function create view model, which creates a real search view model. And then we validate based on where we are, whether there's suggestions or not. So initially suggestions are empty. We set that text to coffee, and then we validate that there are some suggestions back. In this case, a specific number. So let's look more at how that mock was created. So on the left, you can see Kotlin is using mock K. That's the library that we basically get everything for free. And so it's returning the pass-in results for each of the various geocode overloads and the suggest call. And then on the right, you see in Swift, we create a locator task mock. So I mentioned before, we generated an abstraction around the SDK with protocols and mocks around each of those types. So this locator task mock is our ability to mock that locator task protocol. And so we create that mock, we pass in the same results, everything looks pretty much the same, save for maybe some syntactical differences and some argument names. And so just in this simple, very, very simple implementation of a search view model, you can see we had a number of tests covering a variety of combinations of inputs from the user or scenarios that they could get into. These tests, they give us the confidence that the business rules that we had around this are accurate, and that we've implemented them correctly, and that they won't change unless we explicitly want them to. It also helps ensure, when you find a bug, we create an issue, we have a bug that we were going to fix, we create a test for that specific bug. So that way when somebody comes into that same code 6 months down the line and fixes some other bug, they don't accidentally reintroduce the same bug. So yeah, that's a list of just the tests for this particular view model. As of today, in field maps with our rewrite, we have over 3,500 unit tests on each platform across all of those modules. And so I think we're pretty confident and happy with this new approach and where we are going forward. And that's...
Yeah. We'll remind you again to please share your feedback. In the app, we have these links if you want to reach out to Esri or find out about Esri events, and then we can open it up to questions, if there are any. Yep.
You mentioned a major rewrite. Is this part of that major rewrite, or is this something else that you're doing now? You mean
the app that we were showing?
Yes.
That's just something we did like yesterday, just to sort of.
Well, no, I mean, like build, the rewrite is assuming a build map.
Yeah, right. Okay, I'll give you to answer that question. The question is like, what is this something we're doing today? So we had that slide where I had a bunch of different apps listed out. We had a bunch of apps, and we decided that there was a lot of overlap, and there was also some demand from customers to say, hey, I want to have, this functionality from this app and this, and I want it in one app. So we actually, in 2020, we started to build field maps by putting together the apps like Explorer, Collector, and Tracker. And so that actually was a project that we did. We've released it. It's actually been the most successful app Esri's ever built. But this thing that we're doing now, the Sequoia project, is really just rewriting that, because those two code bases were so different. And yeah, I mean that's I guess.
That you're using them, I guess, that you're still going with the Swift and the
Yeah.
for those.
Yeah.
Do you find it important to have that native UI feel? I guess.
I think we do. I think that there's a lot of it's not like there's types of apps where people just, kind of show up and have to use the app. And I think, but for field maps in particular, the people that are using it they're not GIS people at all. So they're just coming at it from knowing other apps on their phone. So it's really, I think, helpful to them if they don't have to learn our app beyond the stuff that our app does, if that makes sense.
Yeah, it does.
Yeah. Yeah.
So I'm just kind of curious, like, who decides on, like, how do the naming conventions and all this stuff get decided? Like, you're got two separate teams, and unless they're working side by side and looking at what each other's naming conventions are, like, how does that get decided?
Yeah, that's a good question. How do we decide on the naming conventions? It was a process, to be honest, because it was two separate teams, two different opinions about a lot of stuff. We could probably think of many examples where we would make a decision about the naming thing. And then, so what happened was initially when we started this project, it was initially like a research project that went a couple of months, because we were new to the declarative UI, and we wanted to make sure that this was something that actually could be accomplished. And then after that, we started adding people to the team and grew the scope. And it was like every time we added new people to the team, and once they got up to speed with stuff, then they'd be asking like, well, why are you guys calling this, and why? So we have a regular touch point where all the developers are there, and that's an opportunity that happens every week. It's an opportunity for people to talk about naming conventions, anything really, patterns and stuff. And then a lot of times it's just a discussion, and we have to make a decision.
Yeah, just a couple things to add. So initially, we identified certain things that we just said, well, those are platform differences. Like, we'll just say those are accepted, right? You could use, an example of that is the way we assert values in our tests. Android had a function called assert that, assert equal, whatever. And on iOS, we used XCTest framework, which is an Objective-C framework. And there are no namespaces in Objective-C. So all of the API are prefixed with usually 2 or 3 capital letters. So our test functions were XCT assert equal. And so they were different, but we said those are the same. Well, over all this time we've been doing this, we keep adding some well-known things. And so now we've got this long list. And so we've started kind of going back and coming up with common conventions and renaming all those things. So the example of the assert functions, we actually just recently went through and added wrappers on the iOS side and automatically changed everything to use those so that the code lines up exactly. And so we're slowly kind of reining in some of those well-known exceptions.
Yeah, another example, I remember that when we first, early days, we didn't call the views on the Kotlin side. So on the Swift side, when you're doing Swift UI, that is a view. But on Kotlin, it's not a view. And because when people talk about Android development and views, it's the old way of doing things. It's like no Android people ever say view. So we had to just, for a while, we had a different, name. What did we?
Screen?
Screen. I think we called it screens. And then eventually, again, it was like, well, they don't look like they line up. So, all right, we can just accept that it's a view and we're okay with it. So, and now I don't even think about it. So, yeah.
Do you find a lot of cultural resistance between like traditional iOS developers and Android developers that really want things to be the way they're used to it, and now there's a tension?
That's a good question. The question is there, would you say cultural, did would Android developers and iOS developers, be opposed to doing things this way? I haven't seen that. And I think that the code that we're writing looks a lot like all the code you go out to, like when you go to, I want to go look something up like on google.com, and it's like, okay, this is how Android code looks. So I think we're pretty much in line. There's probably a couple things, but there is still a tendency or a desire by some developers to just do things the way they want to do things. Maybe it's different. It's definitely different between developers, and maybe it's more different on one platform than the other. I don't know if iOS you feel. I know there are a couple constructs that we try to avoid on each platform, and that might be an area where you'd get some resist. Like if we brought in an Android developer and they're used to using, what was the one we just took out of the example? Also, yeah. Also is super handy, but there's no equivalent on the iOS side. I know iOS we have like guardlet and iflet. So, but we haven't, to answer your question, we really haven't had a lot of pushback. Maybe some initially, but people got over it.
I think once people start to see the benefits of having this stuff align and how much easier it is and how much less friction you have by going with it, it starts to become a little bit easier to accept.
And the practical results, because we've been doing this for a couple of years now, it's a massive undertaking, right? But we've got this whole team of people, not just the developers, that are bought into it, how we're doing the testing and so forth. And to see that when a bug gets found on one platform, the first inclination is, okay, let's go see if it's there on the other platform. It almost always is. Any other questions? All right, well, thank you all for coming, and have a good rest of the conference.
Thank you.